Welcome to the third and final part of a three-part series explaining nuclear power. In the first part, we went over the basic overview of nuclear power, and in the second part, we reviewed the past and present timeline of nuclear power. If you haven't seen those videos already, I suggest you see them before this one. In this section, we will talk about the future of nuclear power and what companies are doing to make this dream a reality. The journey of fusion research is a tale woven with both breakthroughs and setbacks, combined with international collaboration and competition, tinged with drama and intrigue. Achieving nuclear fusion is an extraordinarily challenging task. This is like creating a star in a lab. As explained in the previous video, to initiate fusion, the hydrogen nuclei must be heated to extremely high temperatures, around 100 million degrees Celsius, just to enable them to move fast enough to collide and fuse. Additionally, they need to be confined and compressed to a high density to sustain the reaction. These demanding conditions, known as the Lawson criterion, necessitate significant energy and technological capabilities. There are two main techniques to achieve the Lawson criterion and consequently fusion. The first one is magnetic confinement. Magnetic confinement is a technique to achieve nuclear fusion. In this method, the fuel is transformed into plasma under the influence of extreme temperature and pressure in a small core. The plasma particles are caused to fuse and undergo fusion under a magnetic field. The International Thermonuclear Experimental Reactor, or ITER, located in France, was conceived in 2007. It united unlikely partners including the European Union, the United States, Russia, Japan, and China, with India and South Korea joining later. With an estimated cost of around $22 billion, the ITER project is a joint-sized experiment that uses magnetic confinement to generate 500 megawatts of fusion power for at least 400 seconds. This would achieve a tenfold gain in plasma heating power. The extended fusion period would mean fewer reactions are needed to supply the consistent power, which is an important consideration considering our limited ability to store energy. Laser inertial confinement is another method that scientists at the Lawrence Livermore Lab use to achieve ignition and Lawson criterion. It involves focusing many lasers. In this particular experiment, 192 in total, focusing on the walls of the diamond tube holding the fuel material, which is a mixture of isotopes of hydrogen, including deuterium and tritium. After we achieve the Lawrence criterion and ignition, the important consideration is to break even or to have more energy output than we input. The Lawrence Livermore Lab in California is the only experiment to have achieved that so far. This was a huge achievement and was celebrated all around the world. The US government, DARPA, posted an interesting analogy about it on their eWeb blog. When we apply a match to a wood stick, if we compare the energy from the input to the burning stick, we anticipate far more energy from the burning stick. Similarly, in the Livermore Lab's recent experiment, the energy released from the fusion fuel or the wood stick exceeded the laser energy or the match, passing into the vacuum vessel. In this analogy, the issue that we now face is that our match is extremely expensive. All that is needed is a more economical and efficient match. The issue of maintaining a flame is no longer holding us back. Furthermore, The post compared the importance of this result to our ancient ancestors' earliest achievement of controlled fire. At an unknown time in the distant past, an individual released more energy from burning wood than the input energy of sparks leaping from their flintstones. This ability to bring forth fire at will is the first step towards sophisticated human control of chemical combustion. Similarly, we expect this demonstration of scientific energy gain in a fusion experiment and rapidly progressing work in other areas of fusion research and development to open a pathway towards utilizing fusion energy in producing clean, on-demand, economical heat and electricity. Another key challenge facing fusion research is the availability of fuel. Deuterium is abundant and is commonly found in our oceans. We have a seemingly unlimited supply of deuterium. Tritium, on the other hand, is a rare and radioactive isotope of hydrogen that is crucial for fueling fusion reactions. While some experiments like ITER rely on external sources of tritium, many newer experiments are trying to achieve self-sufficiency through advanced tritium breeding modules within the reactor. These modules utilize neutrons from fusion reactions using lithium to produce more tritium, ensuring a sustainable fuel supply for fusion power plants. These and other technical challenges in the complex design of fusion reactors have only recently been solved with substantial computational resources and intellect. For example, an ideal magnetic field shape is required in magnetic confinement, and in inertial confinement, the efficiency of the lasers is still to be improved. The break-even point does not consider the efficiency of the lasers, and the laser energy of 2 megajoules required more than 2 megajoules of electrical energy due to the inefficiency of the lasers. The lead researcher at the Lawrence Labs has already proposed a new, improved direct drive method for the experiment for future designs to increase energy transfer and efficiency to the laser. The promise of fusion energy in the coming years is important to guide the world towards emitting fewer harmful gases in the production and use of energy. While fossil fuels have powered much of our past, they also create greenhouse gases and pollution. Russia's recent actions have shown the need for more energy sources beyond limited fossil fuel options. Research, government investments, and startup investments to commercialize fusion technology has been on overdrive in the past few years. According to Dealroom.com, in 2022, on the private side, companies trying magnetic confinement received investments of over $4 billion US. Companies trying inertial confinement received investments of over $500 million US. And finally, companies trying a hybrid of both inertial and magnetic confinement received $1 billion. Some of the private companies which have been in the news with the most promising technologies are TAE Technologies, formerly known as Tri-Alpha Energy in Lake Forest, California. TAE Technologies is forging the path to cost-effective commercial fusion energy. Through its unique approach to fusion, TAE has developed spin-off applications in energy storage, electric mobility, life sciences, and more to create a complete clean energy ecosystem. It has an enterprise value of over $2.6 billion US. Next is Zap Energy, headquartered in Seattle, Washington. Zap Energy is building a low-cost, compact, scalable fusion reactor with no magnets and the potential for a short path to commercially viable fusion energy. ZAP has an enterprise valuation of around $640 million to $960 million. Finally, we have Helion Energy, headquartered in Everett, Washington. Helion Energy is developing a pulsed non-ignition fusion technology to produce fusion power using deuterium and helium-3. OpenAI CEO Sam Altman has already invested $375 million in Helion Energy. Additionally, Helion has signed a deal to provide energy to Microsoft for its computing resources for AI. Its current enterprise value is the most, at around $3 billion. In summary, the need for energy is expected to triple by the end of the century due to the increase of the number of people, urbanization, and better access to electricity in developing nations, especially in India and China. The emergency demands of AI computing power are also incredibly high. There's an urgent need to figure out an energy breakthrough. Is the solution going to be nuclear fusion? The answer will depend on our ability to innovate and push the limits as humans. Over the course of these 3 videos, we have understood the basics of nuclear power, reviewed the past and present timelines, and discussed the future of nuclear power. If you like this series, please make sure to like and subscribe.